In today's video, we will look at the RP Photonics Q-Switch software, which is used for nanosecond diode pump solid-state laser design. If you work with lasers or interested in lasers and optics, you have probably Googled a lot of different effects and trying to get some more information, and you ended up probably on the RP Photonics encyclopedia. It's a really reliable and nicely described. It's a very nice source of information for all these laser-related topics. If you want to have want to get like a deep knowledge of it and understanding, then yeah, that's some place to start with, definitely. They also have software, yeah, not just the encyclopedia. And also like a buyer's guide if you're not finding any component just by Googling stuff. The software is so there's a couple of different software they use also in the encyclopedia for demonstrations, and I guess all the software is based on the information you're getting from the encyclopedia actually. The Q-Switch, RP Q-Switch software is one of these softwares they are offering. Yeah, you can basically analyze a given setup of your solid-state laser. The software has multiple windows. We will get there. Basically, we'll have a look later. You can plot a lot of things in there for a different for your laser design. You can enter a lot of different parameters. Actually, everything what is describing your resonator. Let's get back to that later. Yeah, so you can design lasers with it. It's a 1D approach. Yeah, so you just have components in your resonator, like typical components, and it's taking these components as boxes or like a single units, taking them their properties and evaluating, the evaluation of the evolution of laser power, pump power, gain, and so on. So it's analyzing basically your system. How to use? So if you want to design a laser, you will or analyze a laser, you have to start with a laser design recipe. So let's say you will have to put have a plan in mind already, how this laser should look like. Then you will have to add the properties of the different components you have in your laser design. And yeah, so like the properties of the gain medium, the properties of the losses, the saturable absorber. Yeah, so the properties of the components. Then you can analyze the model, the cavity with all the different tools they have here, and yeah, then you can start modifying the variables. Yeah, you can use a different doping level crystal. You can use a different initial absorption saturable or passive Q switch. You can play with the losses. You can move these variables so you can so you understand how you get the target pulse energy, what you want to do. Yeah. So I haven't seen it anywhere. The software comes with a manual, but here's the list of components you can add in the model. That's probably a good overview. There was no overview on the manual, but it is, so all the components are nicely described in there. The components you can add is an active Q switch, like a acoustic optic modulator. passive Q switches, all the you can define the parameters yourself, so just need to get it from your supplier. The gain medium you can define, the output coupler mirror, if you want to use a frequency doubler, so like for double the change the wavelength, double the frequency of the output, you can do that here too, and you can add losses. Now these different kind of components in the model are added using these letters. To understand this a bit more, let's have a look at my starting design. So this is what I was thinking about. This is a laser beam output, and this is the resonator here, the cavity. On the right hand side there is the high reflection mirror. On the left hand side there is the output coupler, and this is where the laser beam will come out. Of course, you can put optional amplifier stages, which can be handled in the program as well, but we won't do that for this little test. And then there are all the components inside. They from the right to the left, the gain medium will be an neodymium YAG crystal, pumped by 808 nanometer dyed laser. Then we will have a passive Q-switch, chromium YAG crystal. It's a very popular one. Then we will have some kind of optical assembly. I was thinking that I could use a polarization maintaining fiber, PM fiber, which is also single mode. So I can basically give the cavity a polarization preference and also like a mode preference. I would like the cavity to have like a nice single mode Gaussian output, and I'm hoping that would probably do the trick. So basically a lens coupling the light in the fiber and the lens coupling the light out. And then there would be yeah, okay, so I have to mention that all these components will be not considered in this simulation software. It will be only considered as losses. Yeah, if you couple light into a fiber, you will have a Fresnel reflection loss on both ends. It's like 8%, but you can include other losses here as well. The anti-reflections coatings are not perfect. You know, if there are uncoated surfaces somewhere in the system, you can add that too. Or just a mode mismatch, for instance, or the fiber transmission. Yeah, so there's like a lot of losses here, which you can add just using one number. So like 12%, so 20% loss for the system. And then the last component would be a LBO, the crystal for frequency doubling, and the output coupler. Now, how to add this whole thing to the software later? We will see that you will need to use the combination of letters. The letters and the meaning was on the first slide I just showed you, and the order of these letters will be you start always with O, so you start at the output coupler, and then you go from the left to right to the HR mirror, and then back to the output. Yeah, so the output coupler is an O, the LBO crystal is a frequency doubler, so F. Yeah, so just follow it through here. Then there will be losses, parasitic losses, P. Then there will be an A as a passive Q switch, the gain medium, and then we reached basically the HR mirror, so we'll have to go back. So again, the passive Q switch, the losses, and the frequency doubler. So this is what you will have to add in the software later. There's of course a lot more to to consider when you are building a laser, just to learn the optics and how you will build this cavity and what kind of components, with what kind of yeah, it's like a lot more to consider here, just that, but that's like just a simple model what you start with and which you can analyze in the software later. And I prepared here also a few components already. So if you you will have to enter in the software a few data to your components. So it's good to have these components like roughly selected, so you can go on the website for Edmund Optics or for Exma or other suppliers, where you can just check all these different parameters you will have to enter in the Q-Switch software. Right. So now that we had that, we can go to the Q-Switch software. I already have here like some example design here. So basically there is a main window. Yeah, so this is what you start with always. Depending on if you want to do a passively or actively Q-switched laser, you will have to open the right file. So there is I think two or more different files in the folder. And on this page, you're entering the parameters of the components. Yeah, so you will have the starting condition. Yeah, you will have a pump. Yeah, I selected here 20 watts of pump power with, and I modulate it. You can modulate it here different ways: sinus, triangular, sawtooth. I chose simply rectangular modulation of the pump power with 20 watts depth. Yeah, so this chart, it's probably more visible. Yeah, so it's 20 watts on, off with 70% duty cycle. Yeah, so it's modulated at 20 kilohertz. Yeah, so the time is in microseconds here. So it's on 20 seconds on and off. It's 70% duty cycle. There is a few other things here. Initial conditions, excitation of gain and absorption. These you can all leave at 0. There are other modes here which you can use. This is basically the startup condition. Yeah, so initially there's no power in the cavity. You just turn on the pump and see what happens. The other two modes are also described in the manual. I think the blocked resonator mode would be useful still, which is when the laser is already working. But yeah, I haven't really looked at this yet. If you use the software, you can ask actually the RP Photonics about this to get you the manual if you're interested. Interested in purchasing it. Yeah, so the laser parameters would be the next tab here, or the next section. The output coupler transmission you have to enter. So that's basically the mirror, the transmission of the mirror. You can enter here the amount of losses in the cavity. I added here 20%. Maybe it's not that large, but yeah, why not? A lot of losses. Then you will have to enter the resonator frequency. So this is basically the size of the cavity, I believe. So if you have a 1 meter long cavity, so between the output coupler and the HR mirror, you have a 1 meter distance. Then in 1 nanosecond, the light will travel 0.3 meters. Yeah, so you will have something like 3.3 nanoseconds await the round trip time. Actually, it means round trip, so it goes from the OC to the HR and back. Yeah, so it's what I have here is a half-meter long uh, half-meter long cavity. Yeah, so distance between OC and HR. But you can change that. You know, if you have a shorter cavity, you can also play with that later in the model. Then um, you can, if you have a longer cavity, you can increase this. If you have a shorter cavity, like so, if you it's the frequency. So yeah, you have a shorter cavity, you will have to increase it, right? Yeah, but for now we will just stick to 300. So, and one more important thing, which was already mentioned in the presentation, is the component order. So the components, we talked about it already. You just have to enter here this combination of letters, which will define, you know, how they, in which order the losses, the frequency doubler, and so on, coming after each other. And so the other components, there is a passive Q-switch in the system. You can choose between a fast absorber or a slow absorber. Fast absorbers like the cesium, or the slow absorber, what we have here is this chromium YAG crystal. Luckily, the saturation energy and the is that the recovery time? I think it's the recovery time is already entered here as default, but you can look this up, and you know there's like a lot of literature about it. Maybe it's also on the website of the manufacturer. So this is where you fill in the passive Q switch. You can actually fill in, I think, both of them. So like information, but I don't know if it will result in a good it will give you a good result. So I would say you either fill in the information for a fast or a slow absorber. Or, you know, if you have both, then maybe both. Okay, right. The frequency doubler is the next one. Efficiency, so that's the efficiency of conversion for low signal levels. So the frequency doubling, so it's at low signal levels, it's really low efficiency. Yeah, so as the signal will get larger and larger, the efficiency will go with a given function to 100%. This is how this is simulated here, as I read it in the manual. Because the low signal conversion efficiency is really low, I would say we just start at 0% efficiency at the beginning. Amplifier stages. So at the moment I don't have any amplifiers, but you can enter here amplifiers if you want to. So like up to 3 stages, I believe. And the different stages, if you press F3, yeah, you can edit the parameters for the first amplifier stage. Yeah, so pump wavelength, power, how long is the amplifier, and so on. You can enter it here. So that's basically a pumped gain medium. The amplifier, like if I press F4, then I will get to the second amplifier stage, and F5. Oh yeah, there is a third amplifier stage as well. But yeah, so it's all not relevant because I entered here 0. Now the next one will be, so basically the program will be calculating here the temporal evolution of the different parameters, so output power, pump power, gain, losses, and so on. And you will have to give it a step, yeah. So a step and the number of steps. So if you enter here 1 nanosecond, 1 nanosecond is actually not possible because it always has to be larger than the round trip time, and the round trip time is 3.3 nanosecond at the moment. So anyway, if I enter here 10 nanoseconds and I do 1 million steps, so 10 power of 6, then I will have, what is that, 3 milliseconds, 1 milliseconds, yeah, Oh yeah, max temporal range is 10 milliseconds. It even says it here. So that's very useful. I would say I would just go for the shortest possible. It doesn't take long to do the calculations anyway, so yeah, let's do this. And so that's the numerical parameters. The pulse parameter, so this is basically like a short output here, like it will tell you what is the peak power of the pulse is coming out and what's the pulse duration. You can take you can evaluate multiple pulses. So in this case, I have here like in the one pump cycle, so the one pump turn on. We have here 1, 2, 3, 4, it's something like 5 pulses, and also a little bit coming together. uh, it's probably not an ideal cavity still, but yeah, you can analyze more pulses. So if you say like I want to analyze 3 of the pulses, then the peak power, yeah, that's a logarithmic scale. You have to keep that in mind, of course. They get lower. Yeah, so these are slowly the peak power is getting lower. Yeah, but I just want to see first pulse to analyze the first pulse, and yeah, so that's what it is. So there's a couple of oh yeah, there's one more thing we haven't talked about, and that's the gain medium. So we have defined here everything: the pumping, the losses, the Q switching, but we haven't defined the gain medium yet. So if you press F2, then there's a new window which will appear, and you can enter here, what's the uh, wavelength of operation. Yeah, you can enter what's the pump wavelength, what is the length of your crystal, what is the mode area, so what is the it will calculate for you the waist. Is it diameter or is it radius? Yeah, in the crystal. And there's a few more parameters here you can enter here, you can play with. This is now for the neodymium YAG setup. So if you have something else, yeah, you will have to enter these parameters yourself. But that's basically, I think that's the optics. Dopant concentration, that's the crystal pump. Yeah, wavelength of the yeah, of the mirrors basically. But yeah, you will have to fill in all these parameters yourself. So and then when you have all this, you can start looking at your resonator, the cavity. What kind of pulses does it produce? What happens if I change, let's say, the output coupler instead of 30%, we will do 20%. Recalculate. Maybe it already recalculated it. Yeah, not sure how much what happened. Maybe let's change. Oh wait, it hasn't changed it, huh? Let's make it 50% even. That would be better, huh? All right, here we go. So you can change. You can see how it changes the component choice, your results. Oh yeah, you always have to click on another cell before recalculating or before replotting. Otherwise, it won't accept it. So if I just go in here again and change it, this is 30, just go recalculate or something. Oops, okay, I didn't like that. Okay. Yeah, don't do that. Just confusing the software, huh? Um, let's see, does it work still, or I will have to restart it. All right, it still works. Yeah, so always click in another cell before confirming, before recalculating or replotting anything. Yeah, and then there's like a lot more parameters you can play with. I don't know what happens if I go for 10 kilohertz of modulation. Yeah, what happens if I decrease the pump power? So Okay, do I actually need that much pump power? Maybe if I increase it to 10 watts. Yeah, amplitude. That's a bit confusing here now, but yeah, here you go. So you can change all these parameters and figure out which will you can understand what is happening in your system, and you can achieve whichever pulse duration or output power you want. Oh yeah, here's one more option which you haven't talked about. You can choose which power and pulse duration you want to have. The second harmonic, okay, intercavity, laser output, second harmonic, calculate maybe 0. I'm not really sure why this is now 0, but yeah, let's just look at this laser output. Okay. So maybe one more thing, because we looked at how to set up the system, we haven't looked at yet how to generate all these nice graphs, and this is at the calculation tab here. You have to click graphics, and on the graphics tab you have a new window here popping up, and there's like a lot of already built-in parameter sets which you can plot. So I chose here the which one, the pulse profile. No, I chose the temporal variation in log scale and the pump power versus time. If I get the temporal evolution of gain and loss, yeah, for instance, that would draw that, or we have already the log scale temporal evolution, pulse profile. Pulse profile gives you the pulse profile, of course. Ooh, I think I closed it. Let's get back to it. Graphics. Okay. So yeah, there's like a lot of different things here. I believe it's the repetition rate. I don't know if it makes sense really here to evaluate this, because the repetition rate will be defined by the passive Q-switch. Anyway, so there's a lot of parameters you can plot here. Yeah, is there anything else here? So there is the manual, of course. I must have it somewhere open. Yeah. If you go back to the software and you just click any of these, if you just click F1, yeah, then it will come up with this PDF, 21 pages. And what I found really good in this manual, there's like a little explanation here also, how to set up the system, the explanation for all the parameters, how to define them, a little bit of guidelines. Yeah, maybe you can also use this video to have a little bit of deeper look into this, because if you just have images and text, it's sometimes not really easy to figure out how to use it in reality. But yeah, so what I wanted to say is it's really easy to find the different parameters. So if you go back to the program, all the different parameters are called like a variable, like in a nice programming language. So if you want to find something like gamma FD, you can just go in here and just look at gamma FD. Yeah, here it is. It's a frequency doubler, and how does it work, and so on. So it's really easy to find this kind of information with this words. Yeah, so that's what it is. That's the RP Photonics Q-Switch program. I will play a bit more with it, try to design my own laser, and yeah, if the components are not too expensive or available on eBay, I can just build it myself. Thanks for watching, and see you next time.